Thank you for purchasing a ConsuLab CL-1902 Electromag. We believe that this product will be an excellent addition to your classroom and assist you in improving your students' learning in all aspects of DC electricity and magnetism. Today we will show you some tips and tricks, best practices, and familiarize you with your new product. We will introduce you to each module and component of the trainer, demonstrate ways in which they can be used, and equip you to answer any questions your students may have. Let us presume that you've received your product and removed it from its box. We will now do an inventory of the components. This process has been greatly simplified for you as every component has its own designated place. In one quick glance, you can assure that nothing is missing. You should have the following, broken down into 9 different sections. The magnetic field viewers, the magic box, the materials section, and modules A, B, C, D, E, and F. The first section we will discuss is the materials section. Let us remove the 2 red and 2 black jumper leads, the power supply, the 2 metal rods, and the bar magnet. You can see that by design, any missing component would be obvious. I will return the bar magnet to its home as it tends to be attracted to many objects, and I suggest you also adopt this practice. As I am handling the 2 metal rods, it is apparent that one is heavier than the other. This is of course because one is made of steel and the other aluminum. Your students will perform experiments with both. You'll notice that on the desktop I have an oscilloscope and a multimeter. These are not included, but these are infrastructure that you will require when using the trainer. The second section we will discuss are the magnetic field viewers. Included with the trainer are 2 ways for your students to visualize magnetic fields. The first one is a magnetic field viewer composed of ferrous metal. The best way I find to use it is to lightly tap it against the desktop to align all bars, and then to gently pass it by a magnet or pass a magnet underneath. The second way to view a magnetic field is with the compass. However, with so many strong magnets around, its polarity is easily reversed, so you must be wary of trusting its true polarity. The third section we will discuss is what we call internally the magic box, since this is where a lot of the ConsuLab magic happens. The magic box consists of the main power switch, an analog voltmeter for system voltage, an analog ammeter for system amperage, a system voltage selector switch that permits 10 volt and 12 volt system voltage, a polarity indicating bicolor LED with 2 4mm socket receptacles, a galvanometer with 2 4mm socket receptacles, a polarity switch, polarity status display, and 4mm socket receptacles that permit connecting system voltage to various components. To begin, let us plug in the power supply and turn on the trainer. Now, this is an important note. With this power supply, as each time that it is plugged into a wall outlet, there is a delay before it starts producing DC current to power the trainer. Do not fret, this is normal operation. Just be sure you are not impatient like me, and you will be fine. With the power supply connected, we can now turn on the trainer, and we'll see the polarity display light up. With the switch in the middle, we have 2 vertical lines. To the left, we have positive and negative one way, and to the right, the opposite way. If you leave the trainer unattended for a period of 30 minutes, the magic box will shut down and the display will show a timeout. Now let me demonstrate the protections built into the magic box. If I connect 2 jumper wires from the polarity switch to a load like the motor, with the switch in the middle, no current flows. With the switch to the left, the motor rotates one direction, and polarity is indicated one direction. With the switch to the right, the motor rotates at the opposite direction and the indicated polarity has also changed. But what happens when your students make a mistake in wiring the motor and create a direct short across the terminals? Where's the magic smoke? Well, there's no damage that occurs. There's an incandescent bulb inside the magic box that acts like a shunt and will simply illuminate in the case of a short circuit. While we are already connected to the electric motor, let me also demonstrate the function of the system voltage switch. If we turn on the motor, when we change system voltage, it can be heard, seen, and felt. The 10 volt scale also makes mathematical calculations easier for your students. Let us move along to the 4th section where we will discuss Module A. Module A is the beginning of your students' journey to understanding magnetism as it is applied to modern vehicles. It is comprised of 2 simple coils of wire. There are myriad activities that we can perform using these coils. Each coil has a hollow core. This means that we can insert either the bar magnet, the steel bar, the aluminum bar, our finger, or anything else your students may wish to test or they can be left empty. I will start by using the bar magnet. If we connect the coil A1 to the bicolor LED, and we now move the bar magnet in and out of the coil, we can see electricity is generated. This is also an excellent demonstration to do with an oscilloscope. Now let us do the same demonstration with the galvanometer. We can see that current is induced in the coil. We can also use the coil as an electromagnet. So let us connect it to system voltage and apply current. If I hold the bar magnet nearby and apply current to the coil, it will either be attracted or repelled by the electromagnet. Now let me put away the bar magnet. Using the magnetic field viewer, we can see that with nothing in the center of the coil, not much is happening when we apply current. However, if we insert the steel bar into the coil and use it as an electromagnet, we can see the strength of the magnetic field is greatly increased and now viewable. The same cannot be said for the aluminum bar. Now you may be wondering, why do we have two coils of wire that are exactly the same? Well, they have the exact same number of turns. If I take my multimeter, they have the exact same resistance. They look the same. However, if we look closely and see these arrows, we'll notice that they are wound differently. This is very important. Let us wire the two coils in parallel with the same polarity and see what happens. Using the compass, we can see that their polarity is different, and the only reason for this is due to the winding direction. We can also notice a small indication on the schematic that gives us a clue of winding direction. We will continue now with discussing module B. B1 has the same number of turns as A2, the same number of windings, the same winding direction, and the same resulting polarity. You'll notice that there are added features to B2 where there are two built-in LEDs showing polarity and induced voltage. You will also see a kind of little hint where the other LED flashes momentarily when you open the circuit. It is important to demonstrate that for B1 and B2, they are not connected in any way. We can physically block off between them. There is a large air gap. I can put objects between the two to prove to the students that they are not connected in any way. The magic happens when we demonstrate induction. If I take the steel bar and insert it into both coils, we can now show that current and voltage are being induced into coil B2. We can use an oscilloscope to measure and see the spikes. We can also measure it with our galvanometer. Another aspect of module B is that the number of turns per coil is not the same. We can measure and calculate the effect this has on the coil's function. So we can see how A1 and A2, and then B1 and B2, slowly build the student's understanding of coils and induction. And they build up to the understanding of module C, because in module C we now have a coil inside of a coil, and a permanent multi-bar steel core that is visible from the side. If we bring the wiring to coil C, we can see the effect it has on the multi-core. We can now show more typical coil operation resembling an ignition coil. Let me demonstrate this with the oscilloscope connected to the secondary and the electricity connected to the primary. The next module we'll demonstrate is module D, and it will blow your mind. It is a physical representation and demonstration of the right-hand rule. When we apply current to a conductor, magnetic lines of flux are generated and a magnetic polarity occurs. Now our conductor and the two bars it is supported on are non-magnetic, as they are made of copper, yet it is situated between two very strong permanent magnets. This means that when we apply current and the magnetic field is generated around the conductor, it wants to move. Watch the magic happen. The circuit is a dead short, so 2 amps are flowing through the conductor. This means that it will arc and spark and occasionally weld itself to the supporting bars, but you can just move it slightly to continue the demonstration. You can even hear it arcing as it rolls back and forth. In the 8th section, we will discuss electric motors, F1 and F2. You can imagine F1 as the most inefficient electric motor imaginable. It has one simple set of commutated segments. There are only one pole pair, one coil of wire, 2 permanent magnets. This means the rotor changes polarity every 180 degrees. So when I hook up 12 volts to it, it might just get stuck in one place, or it might start spinning right away. We'll see. It's a bit like a hit and miss motor. Sometimes we've got to give it a little kick. The cool thing is that we have an adjuster for the brush time, so we can adjust it and see the effect on motor speed and torque. Because it has only one pole pair, it is not a very strong motor. It is not strong enough to spin with the handle connected using this supplied O-ring. Speaking of which, these O-rings are very important as they allow you to connect the handle to the motor and allow you to use the motor as a generator, which we're going to do so now. We can see that depending on the direction in which we turn the motor, we can get different polarity. We can also demonstrate this with the galvanometer. The second motor, F2, has multiple commutated segments, so multiple pole pairs. And when we connect it to system voltage, we can see that it spins quite a bit faster and is much stronger than F1. Because this motor is much stronger, we can connect the handle and turn on the motor and see it work with a load. We can also couple the two motors together, driving F1 with F2, so we can generate electricity once again with F1. Last but not least, we have the ninth and final section, Module E. Here we have a generator with permanent magnets on the rotor and the coil of wire as the stator. By simply moving the hand crank, we can generate AC electricity. We can see this using the galvanometer, using the bicolor LEDs, and even better with the oscilloscope. Now here we can see the pure sine wave AC generated. But what if you want to rectify it? We can use one diode to do so, demonstrating half wave rectification. We can also have a set of diodes allowing for full wave rectification. We hope you are now more comfortable and familiar with using the Electromag in your classroom. Should you need assistance, please contact us and our team will be happy to help. Thanks for watching.